Hello and welcome to this video on finding the change of coordinates matrix or the transition matrix between two bases for a vector space. So in this video, I'm going to start off by defining what the coordinates of a vector are relative to a given basis of a vector space, and what the coordinate vectors of a vector relative to a given basis are. Things we've seen in past videos actually. Just redefining those, refreshing your memory, hopefully. And then going into the process of, if I know the coordinates of a vector with respect to one basis, and I would like to find the coordinates of that same vector with respect to a different basis, how could we transition between the two bases? How could we find those coordinates? And I'll go into several examples in which we do this. Find this transition matrix or change of coordinates matrix between the two bases. Okay, so this first page here, again, just a kind of a refresher from the last video I put up, if you've been following along. If not, don't worry about it. Here's some definitions. So we're getting a change of coordinates here. Alright, so suppose we're given a vector called u, vector u with a little arrow above it, from vector space V, and bases, right, these B and C, these are both bases, right? So B is a basis for V, and C is a basis for V, and they consist of vectors. B has the vectors B1 through Bn, and C has the vectors C1 through Cn, right? And they should have the same number of vectors if they both are bases for the vector space V, right, if it's dimension n. Okay, so if both of these are bases for V, that means that any vector in V can be written as a linear combination of the vectors in B or the vectors in C. Right. So that's where we get to the coordinates of a vector relative to a certain basis or with respect to a certain basis. The coordinates of vector u, pardon me, that I was given, relative to basis B are the scalars, say r1, r2, all these are real numbers, scalars, right? Such that u is, r1 times b1 plus r2 times b2 plus all the way up to rn times bn. Right. So like I was saying, we can write a vector from V as a linear combination of the vectors in basis B. And the coefficients, right, the scalars of that, the weights of that linear combination are called the coordinates of u with respect to B. Alright, and then the corresponding coordinate vector of the vector u relative to B or with respect to basis B is denoted by this. Right? It's a little brackets around the vector u with a subscript of the basis B equals, and then it's a column vector, right? Just a vector with n components, and each component is just the scalars, right? The coefficients of the vectors of B in the order that the vectors of B came in. So the coefficient of vector 1 for the first component, vector 2 for the second component, all the way down to vector n. Alright, and what this little coordinate vector tells you too is that if I use the vectors from basis B and multiply each of them by these scalars and add them up, I'll get vector u. Right, take r1 times vector 1 from basis B plus r2 times vector 2 from basis B plus all the way down to rn times vector n from basis B. I should get vector u back. Alright, and then similarly, I have defined the coordinate. Just change B to C and R1 through Rn to T1 through Tn. And I've got the same definitions here for, the coordinates of u relative to basis C, right? So this C with vectors C1 through Cn in it. So the coordinates of u relative to basis C are scalars, instead of the r's, these are different scalars. T1, T2, Tn, that are the weights of the linear combination of the vectors from C that make vector u, right? Such that u equals t1 times c1 plus t2 times c2 plus plus tn times cn. And then the vector that's made up with these scalars as components, right, with these weights as components, is called the coordinate vector of u relative to basis C. Right, and again, it's at the same notation, little brackets around vector u, subscript of C, right, so we're talking about basis C. And then the coordinates again are just the scalars or the coefficients attached to the vectors from basis C, such that if I were to, take the vectors from basis C, multiply each of the vectors from basis C in this order by the scalars in this vector and add them up, I'd get vector u back. Right? All right, so again, I've shown all this in a previous video, talked about coordinates and coordinate vectors. Now here comes the heart of the problem, heart of the video today. Now suppose that we know the coordinates of vector u relative to basis B. Right, so I know the coordinates of u relative to B are, say, 4, 2, and 5. Right? Say I know what those are. Those are known to me. But I don't know the coordinates of vector u relative to basis C. Right? Those other set of vectors. So we wish to find the coordinates of u relative to C. Right, well, I'm going to tell you right now, and I'll go through the process, I'll go through the procedure with you in several examples, so hopefully it's clear after my several examples today. But this will involve finding an n by n matrix, denoted by P. Now you can have, it really depends, they put it this way because of the way the equation looks that I've written here. P, where I'm transitioning from coordinates in basis B to coordinates in basis C. Now again, if you decided to flip this, then I would prefer probably having basis B, arrow C, just so long as as long as the arrow is pointing in the right transition, right? I'm transitioning from coordinates in basis B to the coordinates in basis C. This is an n by n matrix such that, the coordinate vector for u relative to basis C will be equal to this matrix times the coordinate vector for u relative to basis B. Right? So I know this, and I'm going to know this, right? And that'll help me solve for, find these coordinates with respect to C that I wish to find. Right? And this notation here, this P with the, this matrix where I'm transitioning from coordinates coordinates relative to basis B to coordinates relative to C. All right, this P with the B arrow C here is called a change of coordinates matrix from B to C, or a transition matrix from B to C. Okay, and we're going to be asked to find this thing and then use it, and then I'll show you how we're going to use it to help us, find the coordinates of a vector relative to a different basis, right? A basis that we don't know the coordinates of that vector to. All right. So again, I haven't shown you a procedure yet. Right? We'll get into that now, right? In all my examples. So from here on out, I'm just working through several examples where I'm asked to do the following. All right. So whatever set B is and whatever set C is, B and C are bases for vector space V. All right. So each one is a basis for vector space V. And what I'm asked to is find the change of coordinates matrix for the transition from B to C, right? And you can also find a transition matrix from C to B, right? So my vector space this time is going to be R2, right? Two-dimensional Euclidean space. Under standard operations, right, the way you add vectors and multiply vectors by scalars is the usual way, the common way. And here are two bases for R2, right? Here's basis B has the vectors 2, 5, and 1, 2. These are building blocks for R2. Every vector in R2 can be written as a linear combination of these two, and they're independent. And C is also a basis. 2, 1, negative 1, 2. Every vector in R2 can be written as a linear combination of these two, and these two are independent, so these are like, again, some building blocks that would help me create every vector in R2 if I wanted. Now, let's work on the first one. All right. So 1, I want to find this transition matrix from B to C. Right, now in this case that means we know. Right, suppose the coordinates relative to B are known. So the coordinates of, say, a vector u that belongs to R2. All right. So again, this is just I don't want to use a specific vector yet, right? Because what I'm trying to do is find a transition. I'm trying to find a way to change coordinates no matter what my vector is. All right, and then we'll look at specific examples. So that's why I want just a representative here of any vector in R2. So that's why it's a letter u. So suppose so the coordinates of a vector, u belonging to R2 here, are known. And suppose these coordinates are known to be R1 and R2, right? I was using R's for the coordinates of vectors relative to B, and I was using T's for coordinates of vectors relative to C. You can use whatever letters you wish, but suppose these are R1 and R2, right? Meaning that the coordinate vector of U relative to basis B is this vector with components R1, R2. Right. Right. And so what that means, right, when I say the coordinates of U are R1 and R2, and they're known, I know what they are, right? So they're not variables. Right? I don't have to solve for them. Right. What this means is that U. All right, if I tell you this means that the vector u is r1 times the first vector of basis b, so 2, 5, plus r2 times the second basis vector from b, which is that 1, 2. Okay, so that's what that means. And again, r1 and r2 are known values. I'll write that one more time. Right, make that really clear. Suppose these are known values. I do not have to solve for them. Right. So if I'm transitioning from B to C, that means I know the coordinates of B, and I want to find the coordinates of vector u. Oh, I'm sorry, the coordinates of vector u relative to B. Forgot to mention that. Right. This is in terms of basis B. Right. So the coordinates of vector u relative to B are known. Now I wish to find the coordinates of u relative to vector basis C. We now want to find right. So these will be unknown. The coordinates of vector u, right? This same vector, whatever this vector is, and again, this is just any vector from R2, relative to basis C. So now these are going to be, I'll call these T1 and T2. Right, and these are unknown values, right? I would like to solve for these. All right. Okay, so again, this is or basically, if I want to find the coordinates, that means I want to find the coordinate vector, right? The coordinate vector of u relative to C is this T1, t2 vector, and I do not know these. And again, what this when I say this is t1 t2, this coordinate vector relative to c is t1 t2, this means that the vector u can be written as t1 times the first vector in basis c, which is this vector 2 1, plus and then t2 times the second vector in basis c, this negative 1 2 up here. All right, I'll emphasize this one more time, that these are the values that need to be solved for. These are unknown values. I wish to know these. So R1 and R2 are fixed, they are known. T1 and T2 are my variables, the unknowns. All right, so what we're going to do here, how do I find these T1 and T2? Well, look at these. All right, this was using the coordinates with respect to B and the vectors of basis B. This is the coordinates with respect to C and the vectors from basis C. We see how both of these statements represent the same vector, right? Both of these represent vector u. So these are actually equivalent, or they should be. I can set them equal to each other, right? They both represent the same thing. All right, so this here and this here are equivalent. All right. So I set up this equation. I have, R1. Well, I'll have we'll have the unknowns on the left. How about so the ones with the unknowns, T1, because again I'm going from B to C, and again the way they have this written, if you had B to C the other way, I would put the unknowns on the right, but I have B to C with the C on the left, so I want my the coordinates that I don't know, which are for C, on the left. So T1 times 2 1 plus T2 times negative 1 2 should be equal, and then the side, the way you express u with the known coordinates of B, right, basis B, R1 times 2 5 and plus R2 times 1 2. All right. Now, this equation here. Now, right now I have linear combinations of vectors, right? This is a linear combination of the vectors from C. This side is a linear combination of the vectors from B. Right. And again, the only reason I have it this way is because of the symbolism, right? They got B on the right, C on the left. We're transitioning from B to C. Remember, a linear combination of vectors can be written as a matrix product. Right, like this, if you recall. It's been a while maybe, but this left side is the same thing as this statement. The columns here make a little matrix, a 2 1, the columns of a 2 by 2 matrix. And then, so I've got the coefficient matrix, or the coefficients of T1, coefficients of T2, and then times the variables, T1, T2, equals, and then over here, same thing. These are the coefficients of my R1 and R2. Alright, that's 2, 5, coefficients of R1, 1, 2, coefficients of R2, times, and then the variable matrix, or with these constants, these scalars, R1 and R2. And you can double check, Remember, any linear combination of vectors can be written as a matrix product. And you can check, if I multiply a 2 by 2 by a 2 by 1, I would get a 2 by 1 where the first component would be 2t1 minus t2. Wouldn't I get 2t1 minus t2 as the first component over here? So this is good. And then the second component would be t1 plus 2t2. Can you see it's t1 plus 2t2? The second components are the same. And the same for the other side. All right. So now, another way to write this Okay, remember this here, this t1, t2, this is the coordinate vector of u with respect to basis c. And this r1, r2 is the coordinate vector of u with respect to basis b. One more time, this is known, this is unknown. Right, with respect to b I know, I want to find c. So what we have here is a matrix equation. I've got this 2, 1, negative 1, 2 times the coordinate vector with respect to basis c equals, then this matrix, 2, 5, 1, 2 multiplied by the coordinate vector with respect of u with respect to matrix B. And if I would like to solve for this matrix, where I'm trying to solve for this, I want to find the coordinates of u with respect to C. All right, well, there are a couple ways to do this. So I'll say method 1. These matrices should have inverses, right? Because the way you represent a vector as a linear combination of vectors in a basis should be unique. All right, so these should have inverses. So method 1 is, I want to get rid of this. I can't divide by it, it's a matrix, right? But I should be able to multiply by the inverse. So I find the inverse of this matrix, right? And then multiply both sides on the left, right? On the left by the inverse. Alright, so let's say I call this matrix here A. Alright, so I haven't had a capital A anywhere, so that's cool. So remember A inverse. Now it's a 2 by 2. Alright, it's a 2 by 2. Now you can find A inverse a couple ways. One of the ways was to do the adjoint, right, where you have here's A, and then the augmented matrix, not adjoint, and then you adjoin or augment it with the identity matrix. All right, and then you would put this into reduced row echelon form, and then you'd have the identity matrix on the left, and then whatever A inverse is on the right once it's in, pull that up here. Then you'd have the identity matrix on the left. So you see I got A here, the identity matrix here, put it in reduced row echelon form, then you got the identity matrix, and then whatever is over here is the inverse. Or you can use that adjoint matrix method, where you find the determinant of A. Now the determinant of A would be 4 minus negative 1 or 5, so that A inverse is 1/5 times, and then the adjoint matrix would be 2, 2, and then I promise you I know this is negative 1, 1, 1, negative 1 for the upper right hand and lower left hand corner. Alright, and you can double check me on this, multiply this by this, you'll get the identity matrix. Alright, so what we're getting now, so I'm going to multiply both sides by the inverse on the left, right? Order matters when you're multiplying by matrices. So we have, if I multiply on the left by this inverse, we'd have this. The left side, if I multiply that matrix by its inverse, will be the identity matrix. So the identity matrix times this vector here will just be the coordinate vector of u with respect to C, or relative to C, would be 1/5 times the 2, negative 1, 1, 2 times the 2, 5, 1, 2 times the coordinate vector with respect to b, right? And multiplying these guys, and you can do it with a calculator. This is only 2 by 2s though, so not so bad by hand. This would be another 2 by 2. We'd have 4 plus 5 is 9, and then 2 plus 2 is 4, and negative 2 plus 10 is 8, and negative 1 plus 4 is 3, times the vector with respect to b, and multiply by the fifth, and there you go. All right, there's 9/5, 4/5, 8/5, 3/5. All right, and there you have it. That would be called, all right, this matrix right here, this 2 by 2 matrix. This would be called the transition matrix or change of coordinates matrix, right? Because if I know this guy, if I know the coordinates of u with respect to b, all I would have to do then is multiply by this matrix, and it would give me, or what's over here, the coordinate matrix, the coordinates of vector u with respect to c. So here it is. That's the coordinate matrix, the change of coordinate matrix from b to c, and again, b on the right, c on the left, the arrow. Again, if you had it the other way around, you would just switch the arrow. All right, so let's test it out, and then I'll show you method 2. All right, another method for finding this. So let's test it out. All right, see if it would actually work. All right, so suppose, so let's say the coordinates of vector u with respect to basis b are, I'm just going to put in multiples of 5 here because of all these fifths. How about 5, negative 5? Right. Now remember what that means. If I say the coordinates of vector u with respect to basis b are 5, negative 5, that means that vector u is equal to 5 times the first vector from basis b. Now that was way back here. All right, the first vector from basis b was 2, 5. Right. And then minus 5, right, the second constant, the second coordinate, minus 5 times the second vector from basis b. So what is vector u? All right, vector u would be 10 minus 5 is 5, and then 25 minus 10, 15. There's vector u. Okay, let's keep that in mind, that vector u is 5, 15. And the coordinates of this vector, with respect to the first basis b, are 5 and negative 5. 5 of the first vector plus negative 5 of the second vector from b makes this 5, 15. All right, now what I'm going to do is multiply my coordinate vector for with respect to basis b by this transition matrix, or this change of coordinates matrix that I just found. All right. And let's see what we get when we do that. Looking for paper here, sorry. All right, so by what I wrote up here, the coordinates of u with respect to c should be equal to, this 9/5, 4/5, 8/5, 3/5 times the coordinates of u with respect to b times 5, negative 5. All right, let's see what we get. 2 by 2 times a 2 by 1 is going to be a 2 by 1. And you see I'd have 9 minus 4, 5. Right? That's why I picked multiples of 5 here, because of all these fifths. And then 8 Oops, what happened here? Eight minus 3. Oh, yeah, I'm getting coordinates. I'm not getting 515. I was like, oh, this isn't coordinates. I'm looking for, this is the coordinates of u with respect to basis c. My apologies. So 8 minus 3 would be another 5. Let's see if this gives me the same u. All right, so if I'm saying the vector u, the coordinates of u with respect to c are 5 and 5, that means that u should be equal to 5 of the first vector from C. All right, well, the first vector from C, I'm going way back here again. Right, the first vector from C was 2, 1. And then plus 5 of the second vector from C, 5 of negative 1, 2. And let's see what we get here. All right, so this gives me 10 plus negative 5, that's 5. And then 5 plus 10 is 15, and it's the same u I got earlier. Thank you. All right. Same exact u. All right, 515. And you should, right? If you have the coordinates of u and b, I mean, u is not changing. It's just the coordinates that are changing because we're changing bases. All right. So yeah, so I'm given the coordinates with respect to b. So 5 of the first vector in b plus negative 5 of the second vector in b. That gives me the u is 515. I multiply the coordinates in b by that transition matrix, or that change of coordinates matrix. I get the coordinates in c, which mean that 5 of the first vector in c plus 5 of the second vector in c, which is this, should give me the same result. All right, they should give me the same result. So that looks good. So this looks like it's a good transition matrix, a good change of coordinates matrix. Is 9/5, 4/5, 8/5, 3/5 matrix I have here. All right, so that was method 1, all right, where I set up this equation here and then found an inverse and multiply both sides by the inverse. Method 2 is very similar to what I'm doing here. Remember how I find an inverse. Method 2 is I'm basically solving an augmented system here. So I can just set up a little augmented matrix where this matrix is on one side, this matrix on the other side, and then changing it to reduced row echelon form would give me the identity matrix on one side, and then basically the product of the inverse and this matrix, the inverse of the left matrix and this matrix on the other. All right, let me show you what I mean. All right, so method 2. So same thing here. Augmented matrix. So I write an augmented matrix for this equation, this system, because I have two variables I'm solving for, t1 and t2. Or I have 2, 1, negative 1, 2 on one side. Then I put a bar where the equals are, and then this matrix on the other, 2, 1, 5, 2. And so I'll call this matrix A and this matrix, D for now. So I got A here, D here. And when you put this in reduced row echelon form, it's kind of similar to how you found an inverse for a matrix. If I put this in reduced row echelon form, you'll have the identity matrix on this side and then A inverse times D. Right? It was like if I was multiplying both sides like I did earlier. It's basically a shorthand way of multiplying both sides on the left by A inverse, by this matrix's inverse. So I'd have the identity matrix over here, and then let's see what I get over here. And this is our P from B to C. This is our transition matrix, our change of coordinates matrix over here. Okay. So let's see what we get. Now I'm gonna go to the calculator for this. All right. Put in this, this is a 2x4 matrix, and put it in reduced row echelon form. So to the matrix menu, over to edit. This is a 2 by 4 matrix. First row 2, -1, 2, 1. And second row 1, 2, 5, 2. And then get out of here and put in the last entry I put up in the last video, I think, was this reduced echelon form. So I'm just going to put it up again. And there we go. All right. So like I said, the identity matrix on the left half, and you see this this entry here is 1.8. That's 9/5. And then 0.8, that's 4/5. And 1.6, that's 8/5. And 0.6, that's 3/5. So my transition matrix, my change of coordinates matrix, when I'm changing coordinates from B to C, is 9/5, 4/5, 8/5, 3/5. And isn't this exactly what I got earlier when multiplying both sides by an inverse? In fact, this augmented matrix thing, where I have a 2 by 2 on this side, 3 by 3, 2 by 2 on this side, or if it was 3 by 3s, putting it in reduced echelon form is equivalent basically to trying to find what would happen if I multiplied both sides on the left by the inverse, right, like I did earlier. And you see this is exactly the same as I got earlier. Right? The 9/5, 4/5, 8/5, 3/5. Okay. And I personally like doing this better because I can go to the calculator more easily. Especially with larger matrices, 3 by 3s, 4 by 4s. Finding inverses of larger size square matrices by hand is a little more difficult. And just you could put this in reduced echelon form by hand as well, right, with raw operations. But I just like popping things in a calculator, especially when things are large. Right. All right. Now that was the transition from B to C. What about the other way around? All right. Because I did ask for find the transition matrix, from basis B to basis C. So I just did that. Now let's do part 2, right, where I find the transition matrix from C to B. Right. So the transition matrix from C to B. Again, if you have the stuff with C on the right and stuff with B on the left, you write it this way. But if you want, you can put the stuff with C on the left and stuff with B on the right and just change the arrow, right? Go C to B, write it going from left to right instead. All right, so this time the coordinates in C are known, and I want to find the coordinates of the coordinates of a vector with respect to C are known, and I want to find the coordinates of that same vector with respect to B. So this time the coordinates of vector U, belonging to R2 again, are known with respect to or relative to with respect to basis B. I'm sorry, C are known. C are known. All right. And we want to find, all right, so this is known. Sorry. This is known. And this was that, T1, T2. All right. So back, I'd set up the same equation. All right, I'd be setting up the same equation that I did earlier, so nothing would really change. It's just I want to have the, so I set up this same equation would come back. I'm just going to switch the sides so that the notation means something, right? So the C stuff on the right, B stuff on the left, all that same stuff I did earlier. If you want to look at that again, I'd set up the same equation with these same two matrices, just with the sides switched. So I'm going to write that again. All right. So we'd eventually get down to this equation where I have matrix And I'm going to put the B stuff on the left, the C stuff on the right, so the notation makes sense. All right, so 2, 5, 1, 2 times, and then the coordinate vector of u with respect to B, right? These are the B vectors, right? Equal to, and then the matrix with the columns 2, 1, negative 1, 2 times the coordinate matrix with respect to C. All right, and this time, again, this is known, and I'm trying to solve for this. Okay, and so it's the other way around. This time, I'm not going to do both methods this time, but this time I have this matrix here, this matrix here. I would like to get rid of this matrix to get the coordinates with respect to B alone, solve for these. So I would multiply both sides by the inverse of this. All right, which again wouldn't be too hard here because it is a that wouldn't be that hard actually with the 2 by 2. So again, let's say I call this A, matrix A. A inverse, right, A inverse is just, the determinant is 4 minus 5 is negative 1. So negative, and then 2, 2, negative 1, negative 5. And I'm sorry, there's a lot of noise here. All right, sorry about that. So the inverse of this matrix would be a negative 2, 1, 5, and negative 2. And you can check that out. Multiply this on the left, or multiply these two matrices here. You'll get the identity matrix. And then I'm going to multiply both sides on the left by this matrix. Right? So on the left side of that, on the left side of that. That'll create the identity matrix over on the left side. So I'd have just the coordinate vector with respect to basis B equals, now if I multiply this by this, I'll get a 2 by 2 matrix, and I'm just going to kind of say it here. So you'd have first row, first column, would be negative 2 times 2, so negative 4 plus 1, negative 3, and then first row, second column, 2 plus 2 is 4, then 10 minus 2 is 8, and then negative 5 minus 4, negative 9. All right. Okay, and then times the coordinate vector with respect to C there. All right. Now, this would be called, or this 2 by 2 matrix here. This is going to be my transition matrix P from C to B, right? Because if I know the coordinates in C, I can then just simply multiply by this matrix and get the coordinates in B. Right? And hopefully you can see that this matrix and the one I had earlier, right, the one with the transition from B to C, the 9/5, 4/5, 8/5, 3/5, what you'll notice is that this matrix and this matrix should be inverses, right? Because if you look at this, if I multiply if I found the inverse of this matrix, right, and multiply both sides on the left by it, I'd have UB alone. So the inverse of this matrix would be the transition from C to B, right, which I'm getting right here. All right, so let's test it. All right, and I'll write all these notes also about what things are inverses of what after the example's over. So let's test this. So suppose I know that the coordinates of some vector in R2 with respect to basis C, say those so is equal to like 3, negative 1. Why not? Just make something up. All right. So remember what this means. This means that u equals vector u is equal to 3 times the first vector of c. Now the first vector of basis c was 2, 1. And then minus 1, right, times the second vector from c, which was negative 1, 2. Alright, so vector u that's being talked about here is the vector with component 6 plus 1 with first component 7, and second component 3 minus 2, second component 1. Alright, so there's vector u. And I should be getting the same thing when I find its coordinates with respect to basis b. Alright, so now I take these coordinates with respect to c and multiply it by our transition matrix here. Alright, so our coordinates of this same vector with respect to basis b should be equal to negative 3, 4, 8, negative 9 times this 3, negative 1. Let's see what we get. So the first component, negative 9 minus 4, negative 7. Negative 9, no, negative 9 minus 4. Wow, negative 13. What am I thinking? So negative 9 minus 4, negative 13, and then 24 plus 9, 33. All right. So negative 13 and 33 are the coordinates of vector u with respect to basis b. Now let's see if that works out. So according to this, vector u, should be equal to negative 13 times the first vector from b, which was 2, 5, plus 33 times the second vector from b, which was 1, 2. And let's see what we get. That's negative 26 plus 33, that is 7. Fantastic, it should be 7. And this is negative 65 plus 66, that's 1. It's exactly the same as I expected it to be. So this matrix is indeed the transition matrix, the change of coordinates matrix from C to B. All right, and as I mentioned earlier, a nice note here. The transition matrix from B to C should just be the inverse of the transition matrix from C to B. All right. Okay. Because again, just look at the, look at that thing I had earlier. All right. If you were to solve for the coordinates with respect to B here, you would find, just find the inverse, and the inverse of this matrix would go on the left here, and then that would be the transition from C to B. So the inverse of the transition from B to C is the transition from C to B, and vice versa. All right. Okay. Lots of stuff going on there. One other thing to point out, something that's going to make the next examples a little shorter, right, make a little shortcut. Notice the equation that I set up. The matrix multiplied by the matrix that was multiplied by the coordinates with respect to B. Look at the columns. All right, this matrix back here with the coordinates multiplied by the coordinate vector with respect to B. Look at the columns and look at the vectors of B. These are just these columns are just the vectors of B. And then look at the other side. See this matrix multiplied by the coordinate vector with respect to C. Look at the columns. They're just the vectors of C, 2, 1, negative 1, 2. All right. So I'm going to write this for a general change of bases. Right. So in general, for Rn, all right. So for Rn, right, if we're dealing with Rn, this is R2 here. So for Rn, we'll have what I call, we'll say that m with a subscript of b times the coordinates of vector u with respect to b will be equal to some matrix with respect to c times the coordinate matrix with respect to c. All right, where the columns of MB are the vectors from B, basis B, all right, and the columns of MC are the vectors from basis C. All right, and what you're going to notice is too that you set this up correctly. If you solved for UB, right, the coordinates with respect to B, you'd have, the inverse. You'd multiply on the left. To get this alone, you'd multiply on the left by the inverse of MB here. So MB inverse times MC times UC, right? The coordinates with respect to C. So this would be that transition matrix from C to B. And then the other way around, if I wanted to solve for the coordinates of C, if I knew the coordinates of B, wanted to solve for C, right, and if I wanted to solve for the coordinates of C, I would multiply on the left side by the inverse of MC. Right? So the inverse of MC times MB times those coordinates with respect to B. Right? And then this, that's C to B, sorry. And then this would be the matrix, the coordinate change of coordinates matrix, this MC inverse times MB from B to C. Right? So a lot of stuff here, a lot of stuff. And this was just for Euclidean space. All right, I'll show you examples in a minute where we're dealing with vector spaces that aren't R2 or R3. All right, but I just want to show this up here to make it quick for Euclidean spaces. All right, so my next example. Again, same deal. So I have v equals, we're just R2 again, but I'm going to do the shortcuts with this one, all right, because we're in Euclidean space, R2. One basis B for R2 is, with these two vectors, -3, 4, and 3, -5. Another basis C for R2 has vectors -5, -6, and 7, -8. And like I said, I'm going to say let U be any vector in R2, okay? Well then, according to what I wrote on the last page, this should be true. Right? Then, if I made a matrix, say with these as columns, -3, 4, 3, -5, multiplied by the coordinates of vector u with respect to b, this product should be equal, and then again make a matrix over here. Right, so this is that MB that I was talking about on the last page. And then make a matrix over here where these vectors from C are columns, -5, -6, 7, -8, multiplied by the coordinates of this vector u with respect to basis C. And again, this is the MC that I was talking about on the last page. All right. So if I want to find the transition matrix from, say, B to C, so let's do part one, find transition matrix from B to C. I would try to solve, that means I know B, and I want to solve for C. All right. So this time I'll do that augmented matrix thing where, again, imagine I have this on the left now. All right, because again, C on the left, B on the right. The known on the right, the unknown on the left. Let me make that augmented matrix. Now I know I could do the inverse thing as well, but I'll do that. You know, the matrix for the MC on the left, -5, -6, 7, -8, bar, and then MB on the right. All right. And then we'll put it in reduced row echelon form. And it would be just as though I was multiplying on the left side by MC inverse, right? Which is what I would do if I wanted to solve for the coordinates with respect to C. I would multiply on the left side by MC inverse. And over here, MB, -3, 4, 3, -5. All right, and I'm going to go to the calculator, put this in reduced row echelon form. 2 by 4 again. All right, so -5, 7, -3, 3, -6, -8, 4, -5. Get out of here, go reduce to row echelon form. I'm going to change these to fractions. Okay, so that's it's pretty ugly. All right, and the reason it's actually pretty ugly is because I made these up. All right, I didn't pull them out of a book or anything. I just pulled these. I just made these up. I knew these were bases for R2 because these are independent sets of 2 vectors. All right, so this is yuck. All right, so we get the identity matrix on one side. So now we have the identity matrix on one side, and then over here this would be MC inverse times MB, which is that transition matrix from B to C. All right, and it's this -2 41sts, 11 82nds, -19 41sts, and 43 82nds. All right, so that's it. So this matrix here is this guy, -2 41sts, 11 82nds, -19 41sts, and 43 82nds. All right, so this is what I'm going to use. All right, again, because the fractions are a little nuts with the weird denominators, big denominators, 41, 82. I'm not going to test this one like I did with the last one, but what should happen is if I was given the coordinates of a vector with respect to basis B, I could then multiply it by this matrix, and that the result of that product would give me the coordinates of the same vector with respect to basis C. All right. Okay. You know, I could test it out. Why not? All right, I'll just put in denominators that are like multiples of 41 and 82 here. So let's test this, just with one example. All right, this isn't proving anything, but this is just to verify to myself, make myself believe that this is the good transition from B to C. All right. So let's test this. Oops, I can't spell. All right, let's test. So suppose that the coordinates of a vector u with respect to basis B is known, and say those coordinates are 41 and 82. All right, you'll see why I'm doing that here in a second. All right. Now the coordinates of this same vector, all right, well, first off, let's see what this would be. All right, so what is vector u then? All right, so this means that vector u is 41 times the first vector from B, which was -3, 4, plus 82 times the second vector from B, 3, -5. All right, I'm just gonna punch those in off to the side here. All right, I'm not gonna I'm on a faster calculator. I guess I could do this in my head, but whatever. Negative 3 times 41 plus 3 times 82. So the first component is 123. All right, 123. And then 4 times 41 plus, minus 5 times 82. Negative 246. 6, 6, 6. Okay. So this is vector u. All right, and these are the components, these are the coordinates of vector u with respect to basis b, with the vectors negative 3, 4, and 3, negative 5 in it. All right, now for this vector u, what are the coordinates of this vector with respect to basis c, with the vectors negative 5, negative 6, and 7, negative 8 in it? All right, so I multiply on the left here by this matrix, so negative 2 41st, 11 82nds, negative 19 41st, and 43 82nds. I'm going to multiply this by the coordinates with respect to b, 41 82. Right. That's a 2, sorry. And I should get the coordinates of u with respect to c. And again, the reason I picked these numbers is so the denominators will cancel. Is 9 and 40, basically negative 19 plus 43, so 24. Yeah, 24. All right. So let's see. Is that true? Does this give me the same vector? Is it correct? The correct vector u? So if the vector u, the coordinates with respect to c are 9 and 24, that means that u, vector u, should be equal to 9 times the first vector from c, that was negative 5, negative 6, plus 24 times the second vector from c, that's 7, negative 8. All right, let's see. Negative 45 plus 168. 168 minus 45 is 123. And negative 54, and then minus, let's see, that's 160, 32, 192 minus 54, negative 192 minus 54 would be negative 246. These are the same. So I transition from coordinates with respect to b into coordinates with respect to c, and they both represent the same vector, this 123, negative 246. So that matrix works. That's good. All right, then you could find just find the inverse of this matrix, and that'll give you the transition from C to B, right? This is from B to C. You could find just the inverse of this matrix, or just switch the matrices here, right? If I was to take this equation up here and solve, say I'm going from C to B, so that means I know C, I want to solve for B, so I'm multiplying the left by the inverse of MB, right? I get this MB, I take the inverse of that on both sides. All right, so I leave these the way they are and write the augmented matrix with MB on the left, MC on the right. All right, so 2. Let's find the transition matrix from C to B this time. All right, so again, I set up the augment with B on the left, C on the MB on the left, and MC on the right. All right. And again, this might not turn out so great, but that's negative 3, 4, 3, negative 5, and negative 5, negative 6, and 7, negative 8. And I'll put this into, I'm just going to look at the reducer echelon form here. All right, so back in the calculator, I'll make another 2 by 4 matrix. But just switch it up, negative 3, 3, negative 5, 7, and 4, negative 5, negative 6, negative 8. Reducer echelon form. Oops, nope, I gotta reduce. So back to the matrix. Math, RREF, matrix A. All right. So yeah, something bad again. All right. Well, All right, let's change the fractions. I know those are thirds, 1/3 and 2/3 and all that. So my transition matrix, all right, the transition matrix from C to B is, you know, to the right of the identity matrix. So you have the identity matrix on the left and then that transition matrix on the right. So 43/3, -11/3, 38/3, and -4/3. And there you go. So if you were given coordinates with respect to, you know, basis C, you just multiply on the left by this matrix and it would give you the coordinates for the same vector with respect to basis B. And again, you could test that out with some coordinates that have multiples of 3, just to get rid of these denominators of 3 here. All right, but I'm going to skip that, right? That's good. And this should also be the inverse of this matrix. All right, this was the transition from B to C. The transition from C to B should just be the inverse of that matrix, and you can check that out yourself. All right. Okay. I got one more example here when we're in Euclidean space. All right, then we'll go to some other vector spaces. Again, very simple this. Now that we know it's Euclidean space, I can jump to this statement here. So I'm just going to find, this time I'm just going to find the transition matrix from B to C. And just know that you just kind of reverse everything if you want to transition from C to B. All right, so I'm going to just, again, I know what it looks like, right? You're going to have this matrix, again, I'll call it MC. I want C on the left, you know, B on the C stuff on the left, B stuff on the right, based on the notation, the transition notation. So again, for MC, the matrix, just the columns are going to be the vectors of the, you know, these are bases of R3. These are different bases for R3. So down the first column, 0, 2, 1, -2, 1, 0, 1, 1, 1. And then this matrix times, you know, and again, suppose I have some vector U that belongs to R3. Right? So what are the coordinates of U with respect to C? That should be equal to the matrix, you know, MB, where I have the columns are, you know, the vectors from basis B, 1, 2, 4, -1, 2, 0, 2, 4, 0, times the coordinates of vector U with respect to basis B. All right, and then I would solve, you know, again, these would be known, right? The coordinates with respect to B would be known. I'd want to solve for the coordinates with respect to C. So I'd multiply both sides by the inverse of this MC. Again, a quicker way to do that, instead of finding the inverse and then multiplying both sides by it, is do that augmented matrix where I have MC on the left, bar with the equals, and then MB on the right. And then we put this in reduced row echelon form. Okay, and that'll be equivalent, you know, I'll have the identity matrix over here, so it'll be like I multiplied this matrix by the inverse, and, you know, I'll have done it on, it'll be equivalent to having done that on both sides, multiplying this on by the inverse of this matrix on the left, and this by the inverse of that matrix on the left as well. All right, so this is going to be a 3×6 matrix. Right. So on the calculator, going to edit A again, a 3×6 matrix, first row. So bear with me here. Oops, -1. See, I messed up there. 2, 2, 1, 1, 2, 2, 4, 1, 0, 1, 4, 0, 0. I think those last two are already 0. Yeah. All right, then reduce row echelon form. matrix A. All right, so you can kind of see it. So I got the identity matrix on the left, right there, the identity over here, and then that transition matrix from basis B to basis C is the 3 by 3 on the other side. So you have negative 7, 3, 10, then 5, negative 1 looks like negative 6. Maybe I should scroll over. Yeah, 5, negative 1, negative 6, and then 11, negative 3, and negative 10. All right. All right, and again, we can test this out real quick. I'm going to pick a very simple coordinate, just see how it works. All right. So let's test this. All right, let's test this out. So I'm picking a, now this is from B to C, right? So I'm going to have the coordinates of U. So the coordinates of some vector U with respect to B. Again, this is there's 3 vectors in each basis. All right, so I'm going to do simply 1, 0, 0, right? Something very simple. All right, so what does this mean? All right, this means that U, vector U in R3 here is just the first vector from B, right? 1 times the first vector from B, 0 times the second vector, 0 times the third vector. So the first vector from B is 1, 2, 4. All right, so vector U is the vector 1, 2, 4. All right. Now I multiply this by this matrix. All right, so the coordinates of U with respect to basis C will end up being a 3 by 1. Right? Now let's just envision it here. I multiply this on the left of this. Well, can you see how I just have negative 7 plus 0 plus 0, right? So negative 7, then 5 plus 0. But it's just that first column, right? The first column, 5, and then 11. So the coordinates for this vector U with respect to basis C are negative 7, 5, and 11. Well, let's see if that's true. So this means that U is equal to negative 7 times the first vector from C, which is 0, 2, 1, plus 5 times the second vector from C, negative 2, 1, 0, and then plus 11 times the third vector from C, 1, 1, 1. And do I get this same vector, the same vector U back? And I should. Well, let's see. First components, you have 0, then minus 10 plus 11, that's definitely 1. Then second components, negative 14 plus 5 is negative 9, plus 11 is 2. And the third component, negative 7 plus 0 plus 11 is 4. It works. This is a good transition matrix from coordinates in B to coordinates in C. And if you want the other way around, coordinates in C to coordinates in B, you can just reverse these matrices and put it in reduced echelon form, or find the inverse of this matrix, right? Same thing. All right, now those were for, all these examples here were for, Euclidean vector spaces. I was in R2 and R3. But not every vector space is Euclidean, right? We've seen examples of plenty of others. So this next one I have like just 2 more, right? 2 more. Now, when you're in a different vector space, I highly recommend you find out, or if you don't know already, but hopefully you know the standard basis for that vector space. So here I'm in vector space, the set of 2 by 2 matrices that are 2 by 2. All right, the standard basis for R 2 by 2. This again, the only reason I'm writing this is because it's going to come in handy. Is remember the set of all the 2 by 2 matrices, right, where there's exactly one entry that's 1 and all the other entries are 0. All right, so 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. All right, this was the standard base. Sometimes it was referred to by some fancy E looking thing. I think it's a Greek letter. Or I'll just, I like to just call these S for standard basis. I'll call that basis S, all right, for the standard basis for R2. But that's going to come into play when we set up these matrices and systems and whatnot. All right. So here's one basis, which is the standard basis. So I don't know why I wrote it again. Silly me. Okay, so that's just B. I wasn't even looking. Wow, amazing. All right, so this is the standard basis for R2 by 2. And then we have this other basis, right? These other 4 vectors that span to R2 by 2 and are independent. And like I've been doing, let's suppose that U is some vector, right? Some 2 by 2 matrix, right? Some vector in R2 by 2. Right. Now what we're asked to find, what I'm going to do here is I'm just going to go B to C, right? And you could do the same for C to B. I'm going to find that transition matrix, or that change of coordinates matrix from basis B to basis C. All right, so as before, if I'm transitioning from basis B to C, that means I know the coordinates in basis B. Right? So we know the coordinates of U relative to basis B. All right, and let's call those R1, R2, R3, all the way up to, well, R4. R3, R4. There's only 4 vectors in here. So R1, R2, R3, R4. All right, these are the and these are, again, these are known. I do not have to solve. I'm not solving for these. And we wish to find. All right, we want to find all right, so these will be unknown, the coordinates of U with respect to basis C. Or relative to C. All right, and let's call those, T1 through T4, right? T1, T2, T3, T4. All right, so remember what that means. That means that, if these are the coordinates of U relative to B, that means that U can be written as these scalars times the standard basis vectors. And if these are the coordinates with respect to C, that means that U can be written as these coordinates, these scalars, times the vectors from C. And since they both represent U, they should be equal, right? If they're both representing the same thing. So I get an equation out of this, right? Now again, I'm going B to C, so I'm going to put the stuff with C on the left. So I have T1 times the first vector from C is negative 1, 2, 0, 0, plus T2 times the second vector from C, 2, 0, negative 1, 0, plus T3 times the third vector from C, 3, 0, 0, 4, plus the fourth scalar T4 times the fourth vector from C, 0, 0, 5, 0. All right, and this should be equal to, all right, because this represents U, and so does the, with respect to basis B, with respect to the standard basis, R1 times, 1, 0, 0, 0, plus R2 times 0, 1, 0, 0, plus R3 times 0, 0, 1, 0, plus R4 times that 0, 0, 0, 1. All right, and do you see what we get out of this? Again, we get a nice matrix equation. All right, so I'm gonna, well, okay. we don't technically get a matrix equation out of this, but we will be able to eventually. All right. So what we're seeing here, like if I said the sum of these matrices is equal to the sum of these matrices, right? We need to like make a little setup here, right? We get a system. We get a system of equations that we can eventually write as a matrix equation, which you'll see, right? So if you look at the first row, first column entries, right? First row, first column entries, we'd have negative t1 plus 2t2 plus 3t3 plus 0t4 would have to be equal to, and then r1 plus 0r2 plus 0r3 plus 0r4. Right? That's the first row, first column entries. Then you look at the first row, second column entries, 2t1 plus 0t2 plus 0t3 plus 0t4 would have to be equal to r2. All right. Then the second row, first column, no t1 minus 1t2, no t3 plus 5t4 would have to be equal to r3, right? The only thing with a non-zero in the second row, first column on the other side. And then finally, for the second row, second column, you have no t1, no t2, 4t3, and that's it. No t4 would have to be equal to r4. All right, now you could solve this probably without too much trouble on your own. So again, these are known. I know these values, and I'm trying to solve for the t's. Right. But what I'm going to do here is write this like I was doing with the past transition matrix, the past transition from one basis to another. What I'm going to do is I'm going to write this system as a matrix equation, right, with the product of matrices and variable matrices and all that. So as a matrix equation, this left side, a coefficient matrix. Down the first column, the coefficients of t1, negative 1, 2, 0, 0. Down the second column, the coefficients of t2, 2, negative 1, 0. 2, 0, negative 1. Sorry, that's a 1. 2, 0, negative 1, 0. And the third column, coefficients of t3, 3, 0, 0, 4. And down the fourth column, the coefficients t4, 0, 0, 5, 0. And then this would be multiplied by t1, t2, t3, t4. All right, and this should be equal to, and again, this is not a lot over here, but I can still set this up the same way. Where I have a 4 by 4 matrix again, where down the first column, the coefficients of r1, 1, 0, 0, 0. Down the second column, the coefficients of r2, so there's no r2 up here, then 1 r2, then no r2, no r2, then r3, 0, 0, 1, 0, then r4, 0, 0, 0, 1, and this is multiplied by r1, r2, r3, and r4. All right, so you see the similar setup to previously when I was working in Euclidean space. And these matrices here, right? This t1 through t4, these are this is the coordinate vector of u with respect to c. And this r1 through r4, this is the coordinate vector of u with respect to b. So again, I have a matrix times the coordinates with respect to c equals a matrix times the coordinates with respect to b. It's just the difference is these matrices, the columns are not the vectors. All right, like here were the vectors from the bases. Right here. All right, this was B and C. So look at the columns of these matrices. Now the columns are not matrices, but look at the numbers. Like over here, these should be from basis C, right? So look, negative 1, 2, 0, 0. Look at this matrix from the first matrix from C. Negative 1, 2, 0, 0 as I go down, from the upper left to the lower right. Then 2, 0, negative 1, 0. Look at the next one. 2, 0, negative 1, 0. Look at this third column. 3, 0, 0, 4. Third vector. 3, 0, 0, 4. Fourth column. 0, 0, 5, 0. Fourth vector. 0, 0, 5, 0. What these are, okay, these columns are not the vectors, but they're the coordinates of the vectors relative to the standard basis. That's why, I know it was up here, but that's why I wrote specifically the standard basis for this vector space that we're in. Because, right, like look at this first vector, right? If I take negative 1 of the first standard basis vector plus 2 times the second standard basis vector plus 0 of the third plus 0 of the fourth, I'd get this matrix back. So these here, these columns, and you could have stated that, I guess, for the when we were in Euclidean space as well, but these columns are the coordinates. Right, these are the coordinates, or the coordinate vectors of the vectors in C, vectors in basis C relative to the standard basis. And I'll write this again. Same thing over here, but with basis B, right? Basis B relative to the standard basis. I'll say relative to S first. SB, standard basis, okay? So the columns of these matrices, it's not like in Euclidean space where the columns were the vectors, but the columns are very closely related to the vectors. All right, they're the coordinates of the vectors from the bases relative to the standard basis. All right. All right, and then define the all right, so then what we have, so in general, all right, so like I did with Rn. So in a general vector space, right, so for a general vector space, V, with bases B and C, we'd be able to set up this equation. I'll call this matrix B, but the coordinates of B with respect to the standard basis, right? And S is the standard basis, times the coordinates of a vector U with respect to B should be equal to a matrix, say MC, where again the coordinates of basis C with respect to the standard basis times, and then the coordinates of a vector U with respect to C. All right. So again, I'll write them out where this notation I'm writing has columns that are the coordinate vectors of the vectors in B relative to the standard basis S. Okay. And similarly for MCS, but with similarly with this MCS thing that I've written, but with basis C, right? With basis C instead. C relative to S. Okay. So this is huge. Okay. Let that sink in for a second. All right. So then, if I want to find this transition from B to C, that means I have to solve for this, coordinates. I know the coordinates in B. I want to solve for the coordinates in C. I would need to multiply by the inverse of this matrix, right? Or set up that augmented matrix as before. So going back to the problem here, all right? Yeah, I'm just gonna basically find the inverse of this matrix, because again, I know these are the coordinates in B. I want to find these. I just need to find the inverse of this, right? This is the identity matrix. I don't need to pop that in. So I'm going to find the inverse of this matrix. So go to the calculator here. All right, I might as well do it. All right, so I'm going to make in this case, when I go to edit, I'm going to make an augmented matrix that's a 4 by 8, right? Where this matrix is on the left. Where this matrix is a 4 by 8, right? This matrix on the left, this matrix on the right. Then I put it in reduced row echelon form. All right, so 4 by 8. All right, so we have -1, 2, 3, 0, then 1, and a bunch of zeros. Right, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 0, -1, 0, 5, 0, 0, 1, 0, 0, 0, 4, then everything else is 0 except the last one. 1. Great. And then put this into reduced row echelon form, and we'll scroll over. See again the identity matrix on the left. So it's that matrix on the right, to the right of that, this guy here. Now I'm pretty sure I know all these. Yeah, that's 3/8, and that's 75 thousandths. It's kind of ugly, but yeah. I might as well change it to fraction. Math, change to fraction. Yeah, let's scroll over. Alright, so my transition matrix, the first row is 0, 1/2, 0, 0, and I'll write them down. Okay. So the transition matrix from basis B coordinates to basis C coordinates, right, is equal to this 4 by 4 matrix with 0, 1/2, 0, 0 in the first row, 1/2, 1/4, 0 and -3/8 in the second row, and 0, 0, 0, 1/4 in the third row, and then the last row, there we go, 1/10, 1/20, 1/5, and -3/40. There we go. And again, if you would like the transition from C to B, just find the find the inverse of this, or just reverse these matrices in the augment and put it in reduced row echelon form. Actually, no, you don't have to. It's already this is the transition matrix from C to B. Right? Because if I know the C's, if I knew the C coordinates, I would just multiply by this matrix and it would give me the B coordinates, right? Because this is just the identity matrix. All right, great. So these two should be inverses, right? Okay. Now we could test this out. Now again, the reason that the fractions came up here is again because I kind of just made this up. So yeah, so let's see. I am going to pick again a pretty easy. Yeah, I'll do a pretty easy coordinate. All right, we'll check this. We'll test this. All right. So let's test this out. So say, again, this is transition from B to C. So say I know the coordinates of some vector in this set of 2 by 2 matrices with respect to basis B is 10, 0, 0, 0. All right, four components. And I'm picking something easy here. You'll see why. All right, so what does this mean about U? This means that U is the matrix 10, 0, 0, 0. Right, because it's, remember, B is the standard basis. All right, so it's 10 of this first matrix plus 0 of that plus 0 of that plus 0 of that. So the matrix U, the vector U here, is this matrix 10, 0, 0, 0. All right, and then I multiply. All right, so then UC here will be equal to my transition matrix from B to C times the coordinates with respect to B. If I were to multiply this matrix by this here, I'd just get 10 times the first column. Hopefully you see that. So I'd get 0 and then 5, right, 10 times a half, and then 0 and then 1, right, for the coordinates of this vector, right, this vector U with respect to C. Well, let's see if this works out. All right, let's see if I get the same 2 by 2 matrix back. All right, so according to this means that U would be equal to none of the first vector in C plus 5 of the second vector in C, 5 of that matrix 2, 0, negative 1, 0, none of the third vector, and then one of the last vector, so plus the last vector, 0, 0, 5, 0. And let's see, would this be equal to this? Are they the same? Well, 5 times 2 is 10, plus 0 is 10, great. And then 0 plus 0 is 0. Negative 5 plus 5 is 0, and then 0 plus 0 is 0. Fantastic. All right, so this matrix I have here, this crazy 4 by 4 matrix with all the decimals, looks like it's a good transition matrix from, coordinates in B to coordinates in C. All right. Now, the last example, I'm not going to do a lot of crazy writing. I'm just going to keep this in mind here. All right. Keep this in mind here. How did I form that equation earlier? I'm not going to do this one the long way. All right. So we have one last example where the vector space I'm working with. All right. The vector space I'm working with is P1. Remember, this is a set of all polynomials of degree 1 or less. Now, when I'm working with a basis that's other than, when I'm working with a vector space that's not Euclidean, I'm going to write up the standard basis for that space and use it to make these matrices. All right, set up that matrix equation. The standard basis for P1, right, the set of all polynomials of degree 1 or less, and again I'm calling this S for standard. Now you can go constants to high powers or high powers to constants. I'm going to go X, I'm going to go high powers to constants, X and 1, right? This is the simplest set of building blocks for P1, right? Every polynomial of degree 1 or less is a multiple of X plus a multiple of 1, right? All right, so keep that in mind. And then we should be able to, right, if I want to find this transition matrix from B to C, all right, I'm going to set up this equation here, right here. So on the left, not this one. I'm going to have C on the left, C stuff on the left, B stuff on the right, just to have the notation make sense. So I'm going to have a matrix where I take the vectors in C and I write their coordinates with respect to the standard basis. So I see how X is 1 of the first vector plus none of the second vector. All right, it's 1x plus 0, 1x plus 0 times 1. Then the second vector in C is 1x, right, 1 of the first vector in the standard basis, so 1, plus 2 of the second vector, 2 times 1. So 1, 2. So really just kind of like the coefficients of those are going down. Times the coordinates of, and again I'm going to say let's let any vector u belong to P1 here. So the coordinates of u with respect to C, right? This was from basis C. And the product of these two matrices should be equal to the product of these two matrices, where this matrix is going to be the ones with B now. Right? I got B on the right. So x plus 4, again, I'm not writing x plus 4 down the first column. I'm writing the coordinates of x plus 4 with respect to the standard basis. So x plus 4 is 1x, right? So one of the x's plus 4 1's, right? Plus 4 of the 1's. So the coordinates with respect to the standard basis are 1 and 4. And then x minus 4 is one of these, 1x, right? And then negative 4 of the 1's, right? So the coordinates of that second vector in B is 1, negative 4 with respect to the standard basis, and then times, the coordinates of u with respect to basis B. All right, and now I would like to find this transition matrix. Right? So this is where I know the coordinates of B. I know the coordinates with respect to B. I would like to find the coordinates with respect to C. So I need to find the inverse of this matrix and multiply both sides on the left by the inverse of this matrix, or make the augmented matrix with these two and put it in reduced row echelon form. Okay. Which wouldn't be so bad. I could actually probably do that right out loud. So here we go, 1, 1, 0, 2, bar, 1, 1, 4, negative 4. Now I would take half of this row. I'm just going to kind of do it here. I'd take half of this row first, making that into a 1, this into a 2, this into a negative 2. And then I'd take the opposite of this row and add it to the first row, and then I'd have the identity matrix on the left and then my transition matrix, a change of coordinates matrix on the right. So that makes this into 0, and then negative 2 plus 1 makes this into negative 1, and 2 plus 1 makes this into 3. All right. So my transition matrix from basis B coordinates to basis C coordinates looks like negative 1, 3, 2, negative 2. All right, and let's test this out. All right, this is the last thing I'm going to do. Long video, sorry. Let's test this out. All right, so I'm going to take some coordinates with respect to B here. Just give me some coordinates with respect to B. So suppose the coordinates of vector u with respect to basis B are, and these are smaller, so so 2, negative 3. All right, so what does that mean about vector u? Now vector u this time is a polynomial. All right, so that means that u is equal to 2 times the first polynomial from basis B, right, 2 times x plus 4, minus 3 times the second polynomial from basis B, which was x minus 4. All right, and again, here's basis B up here. Right. All right, and then what is this equal to? That's 2x minus 3x. That'll be negative 1x, and then 8 plus 12, negative x plus 20. All right, negative x plus 20. All right, so hopefully I get that same vector back when I transform it to coordinates in C. All right, so the coordinates of u, with respect to C should again be that transition matrix from B to C. This negative 1, 3, 2, negative 2 times my coordinates in B, 2, negative 3. All right, so this will be a 2 by 1. First component will be a negative 2 minus 9, negative 11. All right, negative 2 minus 9. And then 4 plus 6 is 10. All right. So let's see. Does that work out? Does that work out? All right. So let's see. This if the coordinates with respect to C are negative 11 and 10, that means that vector u is going to be negative 11 times the first vector in C. Well, the first vector in C is x, and then plus 10 times the second vector in C, which is x plus 2. And look, negative 11x plus 10x would be negative x, and then you got the plus 2 times 10 plus 20, And oh, look at that, they are the same. So this is a good transition of coordinates here, change of coordinates. Great. All right, so the key, the most important thing I think from this entire video on change of coordinates, very long one, was this page here. Just the setting up of the equation, and then depending on which transition matrix or change of coordinates you want to do I want to change from B to C? Well, then I need to solve for UC, so multiply by the inverse of this, right? And do I want to change from C to B? Well, I need to solve for B and multiply both sides by the inverse of this, or set up the augmented matrix and put it in reduced echelon form or whatever. But the key is, though, if you're gonna be using this equation here, you're gonna be setting this up, this matrix equation. You're going to need to know the standard basis for the vector space you're in. Which again, if you looked at my video on general vector spaces and bases for a vector space, there was videos out like that in dimension. Bases and dimension for a vector space. Done a lot of stuff in the past where I've gone over Euclidean space, spaces of matrices, spaces of functions, polynomials, and for several of those, I looked at the standard. I talked about that. I named the standard basis. So now, if you don't know the standard basis for a vector space, then you're going to have to go about it the long way, where you set a linear combination of the vectors in B equal to a linear combination of the vectors in C, and then set up a matrix equation from there. Okay, and then solve that. Find the solution to that. So if you don't know a standard basis for the vector space, you're gonna have to do it that long way. All right, so I hope you guys enjoy doing examples, practicing problems of this nature where you're doing change of coordinates, and thank you very much for watching.